PCB and have it made, which I have done, and I'll also show you a couple of elements through that or on that. As always, I'm using another camera or my extra camera, and as we all are well aware, that sometimes causes problem with my audio or video. So if anything happens, it looks like everything is fine. If anything happens, just let me know. Just let me know if something goes wrong. Because I'm going to be using my second camera to try and show you a couple of things. Now, what am I going to be showing you? Hopefully, let's just, okay, I've switched it on. I just want to make sure that everything is working again. Looks like it is. Okay. So why am I using my extra camera? Because yesterday, all of my components arrived, or the ones that I've ordered, and we'll have a look at sort of like all of the components. How do they come? What does it look like? And stuff like that. I'll just show you, talk through it about all these components, because these components, this course is called Build Elements and Layout Design, and part of it is build elements, and the build elements are the electric or electronic circuits. So we're also going to have a look at that. It's like the packaging that they come in and things that you have to think about when you are handling these circuits. And right, so that is that. And once again, if anything happens during the session, if we lose audio or video, just let me know. If I forget to share my screen and you see I'm talking and typing and describing something that you just can't see, just let me know. Okay, so I'm going to be sharing my screen, and we'll start with that. And then as we go through all of these sort of like talking points, then we'll discuss the components as we go through it. Right, so I'm sharing my screen. You should see my Eagle landing page. Let's open up the schematic that I worked on. And I called this the class project 2023, which is now, strange enough. So this is the project that I worked on and finished on Monday. And once again, it was a little bit, probably a little bit rushed, I would say. And it is, but like I said, I wanted to do one and finish it within that time span, just so you can have a good idea of what is happening and what it looks like. Okay, so just a couple of things. Now, these are the components that we looked at in terms of information. This is the 7486. Let me just get that component. 008. All right, it's got to be here. Okay. What you might be wondering is, what I'm doing is I'm looking for the specific component, 86AN. Right. So I specifically took the DIL14 package. And as we spoke about, this IC contains 4 exclusive OR gates. Now, when you order these things from companies, they come in different packaging, but a lot of the times the packaging should hopefully look something like this. I mean, this is a very nice plastic bag where it comes in. It's got the component name on there, and then inside you will have a piece of foam, with the gate. Now I should be, I'm just going to share the image on my little zoomed in camera. So this is a zoomed in of my IC. As you can see, it's got a little dip in there just to indicate the where the number 1 pin is. So we have our number 1 pin here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So this is the dual inline package 14. And as you can see, it's on this piece of foam. And if I take it out of the foam, it looks like that at the bottom. And it looks like that. So you can see it's got the writing SN74LS86AN. That indicates the gate. This is my 74LS8SN. And this is the gate I'm using, and it's the dual inline package, which is a standard package. Now, the package, as we spoke about, comes on this little foam or polystyrene elements, and it's sort of like pushed into that. Now, the reason for this foamy or polystyrene packaging is usually, mainly it's twofold. First, it is there to protect the pins, so the pins don't get damaged while going into being shipped to you or posted to you. And the other is to protect the pins from static electricity. When you are handling these ICs especially, you need something like a grounding strip, and I will share my screen once again. So whenever you work with elements like this, you have this sort of grounding strap that you usually strap to your arm or foot or wherever, and then attach it to a ground point somewhere. I would call this a grounding strap, but a lot of people call this different things, but it is a grounding strap. What does a grounding strap do? Well, it basically takes all of the electric charge that your body might have generated and then discharges it through a ground connection. So usually what you would have is either you would have a anti-static work mat, which is like a rubbery type mat where you have your components and PCB on, and you would have a ground connection on this mat where you would just clip on this strap that you would wear around your arm. Or you would have a laboratory power supply, and it usually has a ground connection as well, and just connect it to that. So why do we use this? Well, your body, as you're moving, you create static electricity. So when you rub your feet on the carpet and you touch somebody else and there's that little shock that happens, that is static electricity, as you are probably well aware. Now, static electricity, it's not really that dangerous, but for electric or electronic components, specifically ICs, it is very dangerous. Not dangerous, but it can damage these ICs quite easily. How can it damage ICs? Well, this is a TTL, transistor to transistor logic, and these pins can only handle between 5 and 6 volts at the maximum. So if I inject more voltage than that, these pins become damaged. And with static electricity, you can create a lot more voltage than just 5 volts relatively easily and without you really knowing it. And if you then touch with your fingers on these pins of the IC, that IC can become damaged quite easily. So that is why you wear a grounding strap, and the grounding strap takes away your static charge and then discharges it through ground, so you do not damage these ICs. Now with static electricity, it is just not, it's not just you rubbing your feet or walking over a carpet, for instance. It is mostly, well, it's not mostly, it is almost, you can also just rub your arms against your shirt, creating a little bit of a charge. And these ICs are normally very, very, very sensitive. So whenever you are assembling things like working with ICs, wear a ground strap or be extremely careful when you're working. Sometimes you also work with a tweezer or some sort of pliers, picking up components and placing it down without physically touching them with your fingers. And it is very easy to damage these components, and most of the time you won't even know that you have damaged them. And so when you move onto your PCB, you insert your damaged components. You don't know it's damaged, and then you will have to test and then find out if your PCB is broken, if your design is wrong, or if if you physically have made a mistake in your PCB, and that usually is very difficult to catch mistakes. So that is why whenever you're working with components, be very, very mindful and careful of static electricity, because it can damage and will damage your components. And like I said, these components are very sensitive to overvoltage. And a lot of people do not understand that static electricity is very, very, very harmful to these very sensitive pieces of equipment. So that's why when you are working with PCBs, you always have a ground strap or something that would take away your static charge. And a lot of these laboratories or offices we work in with PCBs and electronic components will have a sort of like a solid tile floor and no carpets inside, because that static electricity gets generated from everywhere. Right, so I'm sharing back my screen. Oh, well, just before that, so all my components come in these little bags, which are clearly marked, telling you what these components are, what they do. Now, what I will do is I will create my circuit on the breadboard first, which I haven't had time to do as yet. I'll do that first. Test my circuit. Now, as we spoke about, that should have been done first before I actually created my PCB. But I'm relatively sure the circuit should work. Other piece of interest is my little LEDs. I have my TTO regulator. So I'm just going to share my screen again so you have a look. So it is so that is my TTO regulator, and I also have some LEDs, my green LEDs, and also some red LEDs, and then I also have my resistor networks. So as you might remember, my resistor networks, I use these resistor blocks, and those resistors are in a single inline package. So my ICs that I'm using are dual inline package, or DIP, DIP. And that is a very standard package type, meaning that the distance between the pins are all specified by my package type, dual inline package. And I'm using for my resistors a single inline package called SIL, S-I-L, and that's also a very standardized package name, because with that, the pitch, we call it pitch, which is between the two pins, that distance remains standard. Another thing which I'm using, which I haven't mentioned before, are these. I'll show my camera, but just these are these IC connector sockets. And I'll just show one on the screen. I'm not showing my screen yet, so don't worry about it just yet. I'm just setting them up on my screen so we can have a look. So I'm showing my screen and just show you what these sockets look like. So these are dual inline sockets. What they do is that I can use these to insert my IC into. So my IC, my dual inline, it's a nice little, it gives a number 14 there, meaning a dual inline package 14. I use these to insert my IC into. And this is actually the thing that I solder my equipment on. So why do I use these IC sockets? Well, I very rarely, unless I need to, solder my IC directly to my board. Why do I do this? Why don't I solder my IC to my board? Is because at first I wasn't very good at soldering. I wasn't very good at soldering. So that means if I soldered, let's say my soldering iron, which is anything between 200 and 400 degrees Celsius, if you don't know what you're doing, you have to press that against your component, against one of the pins, and then add the solder. Now, because I wasn't too good at soldering to start with, I kept the soldering iron there for maybe a little bit too long, which meant a lot of the heat was transferred to the IC, and some ICs are also very sensitive to heat. So that meant that I also damaged my IC by touching them with solder. Now, if you are better at soldering, you will generally not have a problem with this. But I tend to use these IC sockets for almost all of my ICs and my design. And also the first board that I keep on talking about, this board that I made, I also use these IC sockets. And I'm just showing my screen again. So this is what it looks like with an IC installed. As you can see, the socket is soldered, and then the IC is then inserted into that socket. Now, another thing that also helps with this is that I can, if I can actually do this, I can remove the IC quite easily from the socket. I'm sharing my screen again. So I have just removed the IC from my socket. And now I can replace it with another component or one that is working. So I use these IC sockets quite frequently. And like I said, most of the time it is because it started out with me not being a very good soldering, but I kept working with it or using it just because it is easier to, I'm just putting this IC back in case I lose it. And it's easy to insert and remove the IC. Because let's say you have a element that you are working on, and the IC is broken, then you do not have to desolder the IC all the time, because you will have a. I can close this camera. You can take it off and replace it quite easily. I also have my 9-volt battery, which I'm going to power my circuit with. And it is the last thing I need to show you. Aha, there we go. Here's my battery connector that I'm going to be using to connect my battery. So that is like all the components that I've used. Now, we spoke about IC sockets. You do not need, it is not a prerequisite to use these IC sockets. A lot of PCB designers do not use them. For one, well, you have to buy IC sockets extra. They don't really add any more performance or anything to your circuit. They're merely there to help you if you made a mistake or if the components are broken, so they can be easily removed. But I like using them just because it protects my components and also makes like maintenance to the board a little bit easier. So I do use IC sockets quite a lot, and they are relatively cheap to buy. So whenever I have an IC, I would have the corresponding IC sockets as well. I'm sharing my screen once again. And we spoke about all these other elements where I have my switches. These are my ICs or my resistor networks. And we also spoke about that I missed one resistor. I guess, yes, 1, 2, 3, 4, 5. Yes, I missed one resistor here, but it is not so much of a big problem. And then I have my LEDs and my other resistor network here. I have my AND gates, which is also the same dual inline package 14, also TTL, and also my OR gates. So as we spoke about as well, I create a couple of nets. Oh, this is actually possibly the wrong one. Why do I think this is the wrong circuit and this is not the one that I created earlier? Well, there's a couple of things that might give it away that it is the same circuit, but it's not the one that I created with you guys. Let me, and there we go. Sorry, I'm just looking for that, and I found it. So what I did was a quite common mistake. I did not save my, I did not use a very descriptive name to save it, so I actually loaded the wrong circuit. And this is actually the correct circuit with all the components I've used. Now, the reason why I know I made a mistake is in the previous circuit, I did not have a VCC and a GND net. Now, as we spoke about, I need a VCC and a GND net named and these components created because my ICs that I'm using have got hidden VCC and GND pins. All of the ICs, all of these ICs have a power and a ground pin, and those pins are called VCC and ground. Now, with the elements that I have, or the components that I have used, those pins are hidden, meaning that Eagle connects them in the background. You don't see them, but they are there and they are connected. But the requirement is that you have to create a net called GND and VCC, and then it connects it to that net. Now, in terms of me, or what I have done, just I have my power, my regulator. So my battery comes in through these connectors. That creates a GND. I have a voltage in, which is going to be 9 volts, and then a voltage in, which is 5 volts, and there's a voltage out, and that voltage out is then my VCC connection. So I have created a net. That net is called VCC, and that if you do not want to use it, let's have a look at a different component that you might use. So I'm sorry, I'm not really prepared for this. A lot of the times you can have the actual IC with the pins 1 to 14, and then you have to connect them up. But a lot of the times that creates a little bit of confusion because you don't know exactly which pins goes where or which one connects to what. So I like to use a symbolic representation, but just remember that you have to create a net called VCC and a net called GND, and that is then internally connected through Eagle. But then when you go to the next step, when you create your PCB, you have to be mindful that those connections are actually connected. Have a look at your datasheet. Make sure or ensure which pin is VCC and which pin is ground, and make sure that these pins are connected. But we'll have a look at that as well. But this is where you will have to be aware of your connection, because a lot of the times it will not tell you there is a problem. Because it assumes you know what you're doing. It might give you a warning or something like that, but you have to understand what those warnings mean. So talking about warnings, we have this ECR, electronic rules check or electric rules check. We also have it in, I think, the tools library, and you click on it and it does a error check. Now we do not have an error here, but if you have, I don't want to change a lot of things. This is my V in. Let's say you have a net that's unconnected. Now I deleted this net here, and it comes up with this. It tells me I have an unconnected input pin IC4 on VI, and also give me a warning. So then I will need to know what is going on. Now it's relatively easy. I can just connect these elements back up again. I click on my nets. And connect it, and then rename my net. VN. So when you have or you do the ERC check, you will get a lot of warnings. Either accept the warning or do something about the warning or ignore the warning, but it gives you a good idea of what is happening in your board and what might go wrong. It will also tell you if the if the VCC and the ground net are not connected, but it might get a little bit confusing because a lot of the times it will tell you VCC is not connected, but then you look at your board and there is no VCC connection. But that means you have to create the net VCC, and that connects it automatically. So you might get a warning about a VCC net that it's not there, and then you'll have to create it, and it connects the pins in the background. Now, in terms of exports, there are a couple of things we can have a look at. We can export something called a net list. Now let's just save it in my build and layout design class. There we go. And I've created a net list. Let me just open it up. And this is the net list. It's not really helpful in this version. So what this is, it tells me all of the nets that I have named. My A, B, C, and they're all in alphabetical order. And 1 and 2, 3, 4, A, B, C, C1, CN, D, and ground. You can see ground is probably my biggest connection. And you can see my IC 1, 2, 3, and 4 are all connected to my ground nets. Also I have my VCC connection, and it has my IC 1, 2, 3 connected. You can also check that your ICs are connected. This also tells you all of the pins that are connected. So let's say net A. Now, where is net A? I think it is this connection here. Net A is my A input, and it is connected to a resistor. It is also connected to my exclusive OR gate, and also let's see where else it's connected. It's connected to my IC1 and IC2, which is my exclusive OR gate and my AND gate. It is also connected to the switch and connected to my resistor network band 1. It gives you which pin it is connected to, what that part is called, and also what net it is, and on where is the location sheet. On what sheet. In my case, I only have one sheet, so that is why you will only see one sheet. So you could just use this as well, your net list, to make sure that what you have connected is correct. Also, the ground or the hidden connections is not visible in the sheets, and it will tell you none. And as we spoke about, these are the connections of the ICs made in the background. I can also export a SPICE netlist. I don't need to do that because I don't have any SPICE elements. Remember, SPICE, whenever you see the word SPICE, that has to do with simulation. I can export a parts list. Let's export it here. Let's overwrite that one. Yes, I don't like that one. And this is what a parts list looks like. It tells me all of my components that I have, what their value is, so what their part numbers, what device they are. This is 74LS86N component, what package. So this is dual inline package, single inline package for my resistors. And it just gives you a good idea. So what you can then do is, if you have your parts list, so usually you will use your parts list in two ways. You will use the part list to also order all of your components. So you'll draw your schematic, see what components you need, and then you can use the part list to order your components from the company and get your components like that. You'll also use the part list when you are creating your PCB. You will get your PCB, then you will see, okay, I have a component called R or IC4. What is component IC4? Then you look at your part list, see, okay, IC4 is this this chip. You then select that chip and then place it on your board and attach it through solder. So the part list is relatively important. It helps you with ordering your components and also using that to assemble your board. NetScript we don't need because we're not using this. You can also export an image, but that is just an image of your board. You also have this bill of material. Bill of material is very much like a parts list. It is just a more complete parts list, which you can also save. Let's just save this. I just want to show you the difference between the part list and bill of material. Documents. And save. So on the left side is my parts list, and on the right side is my parts list, and the other one is my BOM or my bill of material. Bill of material, it's got a lot of the information that my parts list has, but it's just got a little bit more of a description with it. Which one you need or use, it's relatively up to you. A lot of people like the bill of material because it gives you more information, what that IC does and what a specific function is. So I would recommend going with a BOM, a BOM list. And it's just bill of material. It just gives you a little bit more information about your components, what they do, what they look like, and so like the package or the device that you have for it. Right. So the bill of materials, as we spoke about, it gives you the part name, the value which you can assign to it, like we named our LEDs green and red, and what devices they are, and also the package and a description. So now, once we've gotten to this this stage, so we've checked our circuit, we've checked the electronic rules of the circuit, we have exported a parts list, a net list, and a bill of material. Now we can switch to our board layer. So we switch to this. So as you can see, I can switch back and forth by this button here. or in File, switch to Board. And it switches to my PCB board. And now you can see we have created our board with a couple of elements, which we will talk through in a little bit more detail. And we can click on manufacturing on this side. And it gives you an idea of what your board looks like. Now, I did make one of the mistakes that I made is here on my top silk screen, this port SLI and the IC for the silk screen writing is overlapping. It's not a problem, it's just an aesthetic thing. If I knew what I was doing, I probably would have moved at least one of these elements like so that they're not overlapping, but I was rushing, so I did not pay attention to detail. Now I did then order this from a company. The company then sent me this. It is a summary. Not all companies do this, but this specific one does. It sent me a summary of my PCB and also a visualizing element of it. So how many did I order? How many layers? The size of my board, what's it called? The material, and also, do I want a solder mask? Do I want a legend? So a legend is the color of the top legend, and that is my silk screen. So this is the top layer view, and as you can see on my top layer, I have that same mistake there. But this is what my board should look like when it does arrive. This is the bottom view. And it can give you all these options. This is the copper itself. And I can look through all of these layers to make sure that what I'm ordering is actually what I am getting. Now, this is relatively important. Not all companies do this, but they will give you, or they will send you a summary of your design and what it looks like for their machines, because they do have their own software that checks your design, but they cannot tell you if your system functions in the way that you want it. So it cannot tell me, oh, you're building a full adder circuit. This will work as a full adder. It'll only check that everything is connected and within the right format. It won't check to see if my circuit is working. That is still up to you to make sure that the circuit you provide them is working. The only thing that the manufacturer cares about is that it is in the correct format. That's all they care about. If it's in the correct format, they will make it. Even if there are very, very obvious mistakes in the board, they probably won't tell you about the mistakes or missed connections. They will just make the board as it, because they assume that you know how to make it. Right. Let's have a quick 5-minute break before we continue on with this. A 5-minute break. And then after 5 minutes, we'll continue looking at these elements. See you in 5 minutes. So, welcome back after our very short break. As you might have noticed, I just sent the link for tomorrow's class. The class for tomorrow again is at the double header class, where we have the class and then a break and then the next class. We'll talk about that in a short while. Okay, so let's have a look at the PCB design, going through a little bit slowly. Slower. All right. So this is our PCB design, and as I just moved my SLI writing. So this, the gray is on the T names layer. So T names layer is the names of wherever the silk screen writing. But you might have noticed, wait, there is something wrong. Why is this not connected? So this connection here is something called a air wire. This line here. It indicates the connection from my V-in pin, from my where my voltage comes in, the specific connection to my regulator. And it is not connected. Now, did I make a mistake? No. What happened was when I switched back to my schematic, remember, I deleted this line here. What happened then, it also deleted the connection that I made in my schematic or my board. Let's call this the board. And I'm then also deleted the physical connection. Now, I remade the connection, renamed the net, but it did not automatically connect my element here. Now, this is something that you have to remember, is that when I'm working my schematic and my board, you can switch between the boards, but please be aware if you make a change in your schematic, that change is then reflected on your board design. So we made a change to the schematic. We renamed, or we deleted and then renamed or remade a net. But then that change is not remade in my board design. Very important, because sometimes you switch between the boards and the schematic and you delete something and then you make a mistake. Right. So what we can do is can I redo stuff? Oh, not that much. Right. We spoke, so these are all elements that we are quite familiar with on this side here. We have our info, our group, moving, mirror, and so on and so forth. And we can have, this is more important what we like to do. We have our route the air wire, so we can click on this. We can click on the layer if you want on the bottom layer or the top layer. And then it connected my element there. So I can connect and drag. And I've now connected those two pins. So you can do that manually. And as you might remember, we can also use the auto router, and you can also rip up. Rip up, meaning that you can delete the wire as well. Now I am sort of like deleting. I'm just deleting a couple of elements which I don't need, or I want to re-show you what I mean, what I'm doing. I can delete all of these wires as I like. Let's see if we can group our elements. Rip up a wire. No, we cannot. When I'm ripping up my A wires, if I select this, usually when you select something, it gives you options. Now, these options at the top, which layer you want to route. I only have 2 layers, top and bottom. If it needs to ignore obstacles, usually walk around obstacles. What that means is it walks around, so it routes automatically around an obstacle and will not wire exactly through an obstacle. So this hole is an obstacle. So if I route with my walk around, it'll route around that. If you see it goes around it, it does not go through it. If I click on ignore obstacles, it like goes straight through it, which is not ideal. I don't like that at all. I usually click on walk around, and as you can see, it walks around that obstacle. Here it goes through it, which is invalid connection. Push doesn't really work that well. It also gives you the options of if it wants to make 90-degree curves, 45, straight lines, slightly curved, or more bendy wires. You can have all these options. What the width of the connection is. Now, we'll speak about that in design rules as well, and also what drill you're using. But we will speak about all that when we design a brand new board from scratch. Also with ripping up, ripping means taking away your copper wires. We can have a trace via polygon, connected copper. So if I connect this, it deletes the whole line. If I have this, it only connects like the straight part of the line. So I still have those elements there, which I can then reroute. All the copper on the same layer. Now you might have a connection via a layer or a via. Now we'll speak about what a via is. So we are dealing with different layers, the top layer and the bottom layer, and we have components connected on both of these layers. Now with through-hole components, I have a thing or a component that sticks through that both layers and basically connects both layers if I add solders on the top and the bottom layer. But if I have SMD components, how do I create a connection from the top and bottom layer? I just want to see if I have a via here. Yeah, I actually do. And that is done with something called vias. So a via, V-I-A-A, so I'll just spell it. A via is a hole between the top and the bottom layer. And that is then filled up with connecting material, either solder or copper, and it connects your top layer trace to the bottom layer trace. Usually the auto router would create these vias. We can also create these vias ourselves. So here we have the via option. So I select a via here. Let's just place it there. I can then connect. Let's say I'm connecting root air wire. The top line, oh, I don't like this. I like this a little bit more. to that via, and then from that via, I can then collect the top line, and it can connect to another element. So that is the via. No, I'm not gonna faff around with my computer with my elements right now. So I can rip up a lot of these times. Usually for me, it's better just to rip up the connected copper, because if you just connect this, you have to click on every single bit which is connected. I like just deleting all the copper, because sometimes you're left with these little elements there. And I can delete all of this quite easily. Now, if I have deleted a component or all the connections of the component, I can then move around that component. If I move around a component that is connected, you can see the connection moves around with it. But it does have certain limitations. And I wouldn't recommend doing this, because then the computer then decides where your connections are done. And you can just, so you have to delete all of these little connections. Now, I'm purposely doing it in this way. You never really ever delete all them at once, because that usually leads up to errors, and sometimes you cannot undo the errors that you have done. So let's move all of my components. Oops, what has happened? I've moved the outline of my board, which I did not want to do. Oh. You know what? I want to speak about the outline of our boards. Let's move that there for now. So it doesn't like me moving this. So what are we going to do? Let's right. So first thing that we usually do when we have a board like this, edit. Is that we usually have a look at our design rules. Now, we spoke about this very, very briefly. It is a very important element that we have to look at. Now, usually design rules are given to you via your manufacturing company. They will give you a recommendation and some design rules. So what are design rules? Well, they are limitations that you will have to follow or incorporate in your design. All companies have got a minimum and a maximum size of your board, and also minimum and a maximum circuits that they can create. So you have to think about it that a lot of these still use drills. So a drill can only be as small. Now, I'm not exactly sure. I can't give you an exact number of how small the drills can be. But the company that I looked at, they have, I think, a 100 micron drill, just a 0.1 millimeter drill, meaning that any holes that I make or the distance to my tracks need to be at least that thick. So you use the information that they give you and then import into your design rules. A lot of the times they will give you these a download, and you can download and import your design rules into your design. But a lot of times that doesn't work so nicely, or it's set up in a different way. So you will have to do it yourself. We'll have a look at layers. Here you can specify how thick the copper layers are, and also how thick the core is. Now you can select what type of material you want your board to be made out of, and also how thick it is. And this will come from the manufacturer itself, and also what your specific board needs to do. Clearance, how the minimum, it also gives you a good description of what all these values do. Minimum clearance between objects and signal layers. So this is the first wire under here is the distance between your wires, or your distance between your connection. So this is the minimum clearance distance. So this is the minimum hole, or the so like this will be given to you by the manufacturer. In this case, I just leave it as these default values, and be aware they are in moles. So that is moles. What is a mole? It's in thousandths of an inch. And it gets a little bit confusing. I keep on mentioning these confusing units, but it's something that you will constantly have to be aware of and make sure that you're not making a mistake. Because a lot of companies still work with moles and inches. That is because a lot of the machines are not made in the USA, but come from United States based manufacturing companies. And those companies on those machines use moles and inches as a default. And a lot of European companies deal with millimeters and microns and micrometers and all those types of units. So you will have to be very, very, very careful now that you are using the correct elements. I usually see, depends on what my manufacturing company tells me, what units they use, or in what units do they give their design rules or their clearance limitations, and then I just use that. Here we leave it as 6 moles. It doesn't really make a difference. We can go smaller, but it doesn't really need to be. This is the difference between the wire and the pad, and also between the wire and a via. So what distance, minimum distance there are supposed to be. Distance between pads, distance between vias, and also distance between SMD pads, and so on. So you can change all of these. And it's important to note that these are now just the minimum distance. So components cannot be closer than the values that you have here. It's not automatically that all the components will be that distance. You just cannot have a, it cannot be closer than this distance. So this is just the minimum distance. Right. This is also another minimum distance between copper and dimensions. So the distance between a copper and the dimension, which is the names, and also minimum distance between drill holes. This has to do with the width of the circuit itself. So how wide it is, what's the minimum drill, what's the micro via, and also a blind via. We'll have a look at all these in a second. But like I said, this is to do with the minimum. These are not necessarily the values that we have used or will be using. It is just mostly the values that it cannot fall under. And we can have all of these other values, which most of the time we do not use that much. We mostly use it, make sure that it corresponds to the manufacturer's values, and then we usually click apply, and then now all of our values are the same. So what is these minimum values? How can I see that I'm encroaching in a minimum value? There we go. It will usually have something like this. Sorry. So whenever you will have a component that you move within another component, it will give you this little red hashed area. Oh, there we go. That's the red hashed area. So that area tells you you have a conflict, and it will give you an error. Right. That has to do with design rules. So I can create a board design. What I want. So the first thing you usually do is create the outline of your board. I do this by selecting a line and selecting the dimension layer. Now this it's very important on which layer you work. Why is it important? Well, for the machines that create the PCB, they look for this information. Your file will also be stored according to the layers that you have created. And the dimension layer is where you will have all of the outlines or the physical shape of your board. That's where all that information is stored. So when you are creating something like that, then you will create or have a specific, you will have to use or work on the dimension layer. You can't work on the top layer or the bottom layer because that is not to do with the physical specification or the size of the board. You will have to work on the dimension layer. So let's select the dimension layer. I select a line. Now, you usually have to start at the origin at 0, 0, and then you can draw your line as big as you want. I usually like the bended line. And I can have my board. And then when you enclose the board or complete the full loop of the board, now you can see that inside of the board is my active area. Here I have a bit of a problem where my one component is too close to the edge of the board, and I just need to move it away. If I click on manufacturing again, it'll give me my board design. Now, with board design, you have options to modify your board shape. So here I have a meter shape. I can click on my elements. This is not working. Why is this not working? I'll figure it out. Radius. So now I have, so what I do is I select the radius of my corner, and I want a round corner. I click on my corner and it rounds off that corner. I can select any radius I want. I want a small radius. It creates a very small corner. If I want a more sharply cut corner, I can meter my way. This is M-I-T-E-R. And that can just cut off the corners or shape your board like you want. It's not that important, but it depends now on what your board is going to be used for. A lot of the times your board will fit into something else. It'll be inside of what we call an enclosure, which is just sort of like the box or the element where your system is going to be housed. PCBs don't generally, unless it's a board like this, are found out, not generally found out in the open. They're usually within something. So if you're designing something for a phone or a phone's PCB, it'll be inside of a case or some sort of plastic covering. Now you will use these options to create your PCB so it fits inside something. As well with the dimension, so I can have odd shaped boards. It does not need to be like this. Let's just delete this. My board can be any shape or size that I would like it to be. As long as it makes a closed loop, my board can have any shape that I want. I can also create shapes or cutouts within my board. Now it has got a hole in the middle, so I can create my boards to any shape or size that I want. What I do I have to say about the size of PCBs is that also have a look at your manufacturer. Usually they will have a minimum size or a maximum size of a board. How they usually work is they have these what we call panels. So they have PCBs about that big, and then they would cut out your PCB from that panel. You'll have a look at the like the minimum size that you can use, or the minimum size that you can get away with, and usually use that. Because the bigger your board, the more expensive it becomes. So I usually have a look at the pricing structure of my PCB manufacturer, and then I see how much it costs for certain sizes of boards, and then just get my outline to fit within a certain size or within a certain price class. But as well, if you're designing for a very specific application, i.e. something must fit within something else, then you don't have a choice. You will have to make it according to a certain size. It's not generally the rule that you want to make it as small as possible. You usually have a board go according to your own specifications. I generally like to use as much size as I want because it just makes, or as much size as I can, make my boards as big as I can for a certain price class. So if I have a look at PCB manufacturers and I'm manufacturing my board, I will see how big I can make it. Just it makes it easier to work with. But if you're designing for a specific application, your PCB has to fit inside something else. You are usually limited to your space. And that will dictate how big the outline of your board is and also the size of your components. So there is no real rule to say how big your PCB, how big or how small your PCB has to be. It is usually application specific. So, and the factors to make that decision is in which size do you fit in your element. So let's say we are speaking about mobile phones. For this mobile phone, I cannot make a PCB that is bigger than the size of the mobile phone. That just doesn't make sense. I can't have printed circuit board sticking out my phone, and making it smaller or too small, it doesn't really make sense because then it'll just be there and then surrounded by lots of plastic. That doesn't make sense as well. So PCB design goes hand in hand with sort of like the design of where it is going to be situated. As well, we can have also with the VIA, we can have a hole. So you can have a certain drill size and create holes. Dimension there. So now I've created these very, very small holes. Usually I would create holes a little bit bigger. Look like that. And you can see I have holes here, but you can add in holes as much as you like. Why would I add in holes to my PCB? That doesn't make that much sense. Oh, it depends on your application. PCBs inside of your phone, for instance, or inside of any type of enclosure, you somehow have to attach that to your enclosure. And this is usually done with something we call standoffs. I'll find a PCB with inside of an enclosure, and then I'll show it to you. Selected page standoff holes. Let's make a note of that. Sorry, just so I don't forget. So we add in these holes so we can fit inside of a enclosure and it can be fitted on. So usually you would have these plastic standoffs, little plastic screws that you will fit your PCB into and then attach with plastic nuts. Why plastic? Because they are non-conductive. You have to remember that your board is copper and usually a very good conductor. And if you are using metal screws and bolts, they can also conduct electricity as well. So if you have a metal screw and you screw it onto your circuit board, it might damage the resin covering and then short out some of your circuits. So you can see the mounting holes. Here we go. On these, and these are for this specifically are standard mounting holes, but I'll have a look and I'll find a good example of a circuit inside of an enclosure. Actually, let me just see if I can find something quickly. Yeah, I'm hoping to find something quickly, but I don't think I probably will. No, I'm not going to find something. Yes, I'm not going to do that because we are running out of time anyways. Right, so we are going through slowly through all the elements we need to go through for this printed circuit board design. This is relatively, I feel, the easy part. A lot of the hard work we do is in the schematic and making sure that everything is connected. And then once that is done perfectly, all the nets are named, all the components are named, we have everything, then we transfer it to the PCB design. Now, the PCB design itself is relatively straightforward. You just decide which board outline you will need to use, what the edges looks like, what mounting option you will have, or how your board is going to be attached to your final product, and then drag in your components and then connect it. That's relatively as simple as it is. And that operation we will continue on tomorrow. We'll create a new circuit, connect that circuit up, and just practice over and over again, creating a circuit and a PCB, and then what that looks like. But like I said, this is the simpler part. The more difficult part, I almost feel, is during the schematic phase, because there you have to make sure that everything is connected correctly and all your circuit functions like it's supposed to, and that you have selected all the correct components. Because if you have not done that, then your life will be very, very, very hard, and you will have to then redo everything that you have done before. So we will, I don't know if my board will be here by tomorrow, probably not, but hopefully by next week I'll have the manufactured board, and then we will have a look at what it looks like and then compare it to our design and see where I have made some more mistakes. Well, I probably did make a couple of mistakes because I was rushing. So tomorrow I've sent the link already. We will continue on with this, but we will create a new circuit from a schematic, take that to a PCB, and then I'll just talk through everything that I am doing and why I'm doing it, and we will create a circuit together. Right. So that is it for today. I will see you all tomorrow. And we'll continue on with our PCB manufacturing journey. Right. Looking forward to it. See you all tomorrow. Bye.